Okay, so we are back again. So this is another example, right? So this figure actually figure I will show you. Figure shows the equivalent circuit of a single phase transformer referred to low voltage side of 200 volt. Calculate the terminal voltage on load, that is on high voltage side, low voltage current and the efficiency, right. So in this problem one thing is that the low voltage side is 200 volt, actually high voltage side 2000 volt, right. High voltage side is 2000 volt. So it is not written here, I have missed it here. So high voltage side you take 2000 volt, that means your N2 by N1 is equal to, it will be 10, right. So that because N2 by N1 is equal to V2 by V1 say. So this will be your 2000 divided by 200. So it will be your 10, right. So based on that we will move. So this is the circuit diagram, that it is referred to low voltage side. So this equivalent circuit of this one for mathematical derivations we have seen earlier. So this low voltage side voltage, look at the cursor, that 200 volt. So this coal loss component resistance is given 400 ohm and magnetizing component it is given 231 ohm. This is the current I0, current flowing through this is IC and through this branch is IM. It is something like you are solving, apart from this turns ratio and other, solving like a series parallel circuit, the way you have done it for single phase. And this is RE1, that is 0.1 ohm and XC is equal to 0.5 ohm, and this is the current I2 dash flowing in the your primary side, and I1 is equal to I0 plus I2 dash, and this is that your 7.9 ohm resistance and 5.5 reactance, that is your what you call the inductive load. It is referred to your primary side, low voltage side, and voltage across the load is V2 dash. Earlier you have seen is V2 dash is equal to KV2, we have already seen it for our mathematical derivation, right. So all these parameters are given. So we have to find out the terminal voltage on high voltage side, that is V2, then low voltage current, that is I1, and the efficiency, right. So that is that we have to find it out. So now IM is equal to, it is a parallel circuit. So IM is equal to 200 by 231, whatever it will come, and IC will be your 200 by 400, right. So this is a parallel circuit. So IM is equal to 200 by 231, so 0.866 ampere, and IC is equal to 200 by 400, so 0.5 ampere, and we know that I0 is equal to IC minus JIM, right. So it is 0.5 minus J 0.866 ampere. So it is actually your I0 is equal to, magnitude will be 1 and angle will be minus 60 degree ampere. Now total load, that this side if you take the total resistor, the RE is given 0.1 and XC is equal to 0.5 ohm, where here your RL dash 7.9 and XL dash 5.5 ohm. So from the primary side, that R total will be RE plus RL, here I am taking RL, right. So 0.1 plus 7.98 ohm, and X total will be XC plus XL, just series addition. So it will be 6 ohm. Therefore impedance Z will be 8 plus J6 ohm. Therefore I2 dash will be that V1, the voltage you are what you call that low voltage side, this is the reference voltage you have taken. So 200 angle 0 degree upon 8 plus J6. So it will come 20 angle minus 36.9 degree ampere. Therefore I1 is equal to, first part, I2 dash plus I0, right. Here in this circuit here you apply your KCL, I1 is equal to I0 plus I2 dash, right. So your, if you do so, it will come, I mean substitute I2 dash and here it is I0. So it will become 20.9 angle minus 38 degree ampere, right. Now V2 dash will be V1 minus R2 dash RE plus JX, your J into XC1. That means here in this circuit what you call, you apply here in this circuit you apply your this thing, your KVL, right. So in this case this is the current I2 dash into your RE plus JXC, and this is the voltage plus minus. So plus V2, I mean this is the voltage, same thing, this is the V2 dash rather, V2 dash, right. So this is plus minus, so plus V2 dash minus V1 equal to 0. So you apply KVL, same thing we have applied there, right. So that means that is V2 dash is equal to V1 minus your, if you take I2 dash into Re plus JXE1, right. So, in that case it will become 200 angle 0 minus 20 angle minus 36.9, right, into that your Re1 is 0.1 plus J 0.5. If you simplify, it will become V2 dash will become, here it is 192.5 angle minus 2 degree, right, and that will magnitude of V2 dash will be 192.5 volt. And earlier we have seen, no, V2 dash is equal to KV2 and N2 by N2, and I told you it is 10 because high voltage side voltage is 2000 volt. I missed that one, it was not written there. So, K is equal to 1 upon 10. So, KV2 is equal to V2 dash, because V2 dash is equal to KV2. So, V2 will be 1925 volt, right, and your what you call that that angle of V2 dash is minus 2 degree, right. So, similarly, your what to this your what you call, so magnitude of V2 is 1925 volt, and next is the efficiency. So, when we will find the efficiency, right, output is V2 dash I2 dash cos phi by phi 2, right. So, V2 dash your, if you look into the circuit, that cos phi 2 dash actually angle between the this voltage V2 dash and difference of the angle between the your angle of I2 dash and your angle of your V2 dash, right. So, if you look into this, that V2 dash I2 dash cos phi 2. So, V2 dash is 192.5, I2 dash 20 magnitude, and cos your angle of I2 dash 36.9 and V2 dash was your minus 2 degree, right. Here we have your what you call V2 dash is minus 2 degree, and here it is your where is I2 dash is minus 36.9 degree, right. So, in this case, so it will be difference only, it will be cos minus theta cos theta, both are lagging. I mean if you take the reference, this is my reference, this is my V1 reference. So, one angle is 30, this angle is 36.9 degree, and another angle is, this angle is 2 degree. So, this is the angle, right. So, it will be 36.9 minus 2, that is a power factor angle. So, that is why 36.92 minus 2 degree, right. So, that is why it is coming your what you call 3160 watt, right. And at the same time, if you see this is the output, at the same time if you make I2 dash square RL, because this is a load power, this power is actually consumed by the load. If you look into that, 20 square into 7.9, it is 3160 watt. So, your answer is correct, right. Now, input power is input that low voltage side V1, current is I1 cos phi 1. So, V1 is your 200 volt, I1 we compute 200 your 20.9, and phi 1 will be your 30, your what you call that angle between I mean if you come to the angle of I1 here minus 38 degree, and your that way V1's angle is 0, it is reference phase. So, it is cos 38 degree. So, that is why it is cos 38 degree, it is 3300 watt. So, efficiency will be output by input. So, 3160 upon 330, so 95.75%, right. So, this is the efficiency of the transformer. Transformer efficiency actually is very high, right. So, another one is that a 500 kVA, this is its full load rating, right, 500 kVA transformer, 2200 your 500 volt. So, high voltage side 2200, low voltage side is 500 volt, 50 hertz, frequency is 50 hertz, single phase transformer has 10% impedance, 10% means it is dimensionless, that means 0.1. I will show you how you can do it, right. It has resistance is given, its resistance is given 0.01 ohm, you have to find out the impedance value, percentage resistance and percentage reactance, but its percentage your what you call impedance is given 0.10. So, how one can do it? Just listen carefully that how you can do it. So, because similar type of problem later you will get it. So, one can do it very easily, right. First you find out the full load current, because this is your what you call full load KVA 500 kVA, this is rated KVA. So, this is 500 into 1000, so volt ampere, and divided by 500 volt, the low voltage side, right. This is full load current at the low voltage side, because 500 volt on the low voltage side, right. So, similarly, if you want high voltage side, you can divide by your what you call, you can divide by 2200, but our say we are trying to find out on the low voltage side. So, it is 1000 ampere, right. Therefore, base impedance will be J, it is called ZB, mean base impedance, right. It will be V2, by I2 FL. So, low voltage side voltage is 500, this is rated voltage, and full load current is 1000 ampere. So, this is my base impedance, right. Based on that percentage is determined, actually percentage resistance, percentage reactance, percentage impedance is determined. So, this is my ZB is equal to V2 upon I2 FL. So, 500 by 1000, so half ohm. So, now let impedance is Z, right. Therefore, percentage impedance will be Z upon ZB. If you assume transformer impedance is Z, then Z by ZB will be your percentage impedance. It is dimensionless quantity, because this Z in ohm, this Z base is also ohm. So, Z by ZB is a dimensionless quantity. So, it will be Z divided by Z base is half. So, 2Z say in this case, and it is given base impedance is given 0.1, that means percentage impedance actually given 0.1. So, 2Z is equal to 0.1. Therefore, Z is equal to your what you call, you find out 0.05 ohm, because here impedance is late impedance is Z, right. So, this is actually Z ohm, it is ohm, right, and this is ohm, this is ohm. So, it is a dimensionless quantity. So, 2Z is equal to 0.1. So, whatever value we will get, that is Z actually in ohmic value. So, 0.05 ohm. Now, percentage resistance we know that R upon ZB, right. So, percentage, so R is given 0.01 ohm, right. So, because this R1 actually this R actually it is given 0.01 ohm, and ZB we have got it half ohm. So, this is actually percentage resistance is 2%, right, 0.01 by half. So, 0.02. So, it is 2%, right, and therefore, x is equal to your, we know no x square, just hold on, we know x square plus r square is equal to z square, right. Therefore, my x is equal to root over z square minus r square, that here it is used, right. So, it is 0.05 and it is 0.01. So, you are getting 0.049 ohm, that is x value, and percent reactance will be again divided by ZB, because this is ohm, this is also ohm, 0.049 by half, it is 9.8% or 0.098 per unit, right. So, this is how one can calculate your this thing. This exercise you do it finding out your what you call that, rather than low voltage side full load current, you will find out that your what you call a high voltage side full load current and base impedance, and try to do it and see what you get, whether you get identical thing or not, right. So, this is your this thing. Now, losses and efficiency. So, in a transformer different types of losses are there, but what we will do actually, we will our main concern will be that iron loss, that is coal loss, that is eddy current and hysteresis loss together, and the copper loss, that is the I square R loss in the winding resistance, right. So, coal loss, these are hysteresis and eddy current losses. Coal loss is constant for a transformer operated as constant voltage and frequency. If voltage is constant, frequency is constant, so coal loss is more or less constant, because we have seen expression for eddy current and hysteresis loss. So, generally variation of voltage or frequency is negligible. So, we will consider that this loss is basically constant, coal loss, right, and copper loss, that is I square R loss, right. So, this loss occurs in winding resistances when the transformer carries the load current. So, actually transformer, if load varies, transformer current I varies, therefore, this copper loss is a variable loss, right. All the time load is not constant, hence the current is not constant, therefore, this copper loss is a variable loss. So, when the transformer carries the load current, copper loss varies as the square of the loading expresses the ratio of the full load. So, generally that actually if I varies, therefore, your loading also varies, right, load also varies. So, sometimes we express square of the ratio of the full load, right, later we will see that. Now, other type of losses which we will not consider in our study, but for our your general knowledge, right, sometimes load or stray loss we call, it largely results from leakage fields inducing eddy currents in the tank wall and the conductors, right. Another thing we call dielectric loss. The seat of this loss actually is in the insulating materials, particularly oil and solid insulators, right, the insulations, right. So, major losses, so we will consider copper loss, coal loss or iron loss, that is Wi, we will assume it is a constant loss, because we assume the voltage and frequency will remain constant. Another is copper loss, it is a variable loss, right, because if load changes, then your what you call that current changes. So, it is a variable loss, right. So, copper loss in the two winding transformer are I2 square R1 plus I2 square R2. I mean, we have seen the equivalent circuit of the transformer. I am going back to one circuit, right. I am going back to one circuit, that your copper loss in the transformer, just hold on, right. Just hold on, we will go back to the circuit, just hold on. Instead of drawing it, I will go back to that here, right, not here, when primary and secondary comes, right, here, right. So, this side, actually this is taken to this side, right. I'll hold on, better just hold on, I'll draw it for you, I have to search it again, I'll go back, I'll draw it for you, just hold on. I'll draw it for you rather than searching, right. So, if you draw the circuit, so this is your what you call my this is core loss component and this is my magnetizing loss component, right, and this is your primary side, say, and this side you have your what you call R1, say, and you have X1, right, and this is your primary side winding, and the secondary side winding, right. If you suppose how I can accommodate this space is, just hold on, let me clear it, I am making it here, just see that whether it is you are understanding or not. So, this is my R, and because of space constraint, so this is my R and this is your this thing, this side is the primary side, right. So, this is the current I1, this is the current I0, and this side current is, say, we are taking I2 dash, and this is my primary winding, right, and this is my R1, and my secondary winding is this one. So, this side is R2, this is X2, and here load is there, say. So, this is R2 and current flowing through this is I2. So, here loss on the total loss is, so magnitude that I2 square into R1 plus your magnitude here I2's magnitude into R2, this is the total copper loss, right, real power loss. So, let me clear it. So, this is what we are writing, that your I2 dash square R1, right, A plus I2 dash square R2, right, total copper loss. So, in this case you just take your what you call I2 dash square common. So, it will become R2 plus I2 dash upon I2 square into R1, right. So, we know that I2 dash by I2 is equal to N2 by N1, earlier we have seen it. So, we just substitute here, if you substitute that it will be R2, and we know we have taken throughout our this transformer thing, k is equal to N1 upon N2. So, therefore, if k is equal to N1 upon N2, it will be R2 plus R1 upon k square into I2 square. Therefore, copper loss will be, say, Re2 into I2 square. This Re2 actually is the equivalent resistance referred to the secondary side, resistance referred to the secondary side. If you take on the primary side, same thing, in that case it will be R1 plus your k square into R2, right, but we have made it on the referred to the secondary side. This is the copper loss, right, this Re2 into I2 square, and this is Re2. So, now let us say x is equal to I2 upon IL, because we are doing on the secondary side, because load is placed on the your secondary side, right. So, say I2 upon I2FL, I2FL is the full load current. Just now we took an example to compute the full load current on the secondary side, that is 500 kVA transformer, we got 1000 ampere. Just now we do one problem. So, same thing mathematically, if you write x is equal to I2 upon I2 into I2FL, I2FL stands for full load. So, I2FL is the full load current that is on the secondary side, right. So, I2 is equal, therefore, from this equation I2 is equal to x into I2FL, right. Now, from equation 1 and 2, so you will get copper loss is equal to Re2, because Re2 into I2 square. So, here you are putting I2. So, Re2 into x I2FL square, right. So, copper loss will be x square into your I2 square FL into Re2. This is the copper loss. Now, therefore, we can assume, we can write that copper loss is equal to x square into WC. WC is equal to I2 square FL Re2, it is called full load copper loss. So, WC is the full load copper loss, right. So, X your what you call that I2 square FL Re2 is WC, it is called full load copper loss. So, your copper loss, then X your what you call copper loss is equal to X square into WC. Now, that is why I have written WC is equal to this much full load copper loss. Now, output of the transformer, so it will generally V2 I2 cos phi 2, right. Now, your V2 is there and I2 is equal to X into I2 full load, that you substitute the value of I2 is equal to X into I2 FL. So, X V2 I2 FL cos your theta 2 phi 2, right. So, in this case I2 is equal to X into I2 FL. So, that means output is equal to X into your PFL. So, PFL actually full load output, right. So, that is your what you correct. For example, suppose if 500 kV and power factor is given, so you can find out PFL, right. So, basically PFL will be V2 into I2 FL into cos phi 2. So, that is your full load output. We also got the current for 500 kVA transformer, kVA was given, that is why, but if you want power in terms of watt, so V2 into I2 FL into cos phi 2, that is the full load output, right, and output is equal to X into PFL, right. I mean if X is 1, then output is equal to your full load output, right. Otherwise, if your X varies, then naturally output will vary, and it will have and it happens for transformer because throughout the day load is changing. So, therefore, input is equal to output plus loss. So, this is my output X PFL, right, plus losses. So, input is equal to output plus coal loss plus copper loss, both you have to consider. So, input is equal to then X into PFL, the output, plus Wi, the coal loss or iron loss we call, right. This Wi you call iron loss or coal loss, plus X square Wc. So, this is equation 5. So, efficiency is output by input. So, efficiency can be written as X into PFL, this is the output divided by the whole term, the input, right. Now, for maximum efficiency, you will take d zeta upon dx is equal to 0. If you say d zeta upon dx is equal to 0, you will see iron loss is equal to copper loss. Therefore, for maximum efficiency, that this condition you have to keep it in your mind for solving numericals. For maximum efficiency, iron loss is equal to copper loss, right. But you this derivative you please do yourself, you will get this answer. So, therefore, for maximum efficiency, coal loss is equal to copper loss, this is the thing. Now, therefore, nu max is equal to, if you put Wi is equal to your X square Wc, right, that means X square Wc is equal to Wi, if you put in this expression X square Wc is equal to Wi, then it will become X PFL divided by X PFL plus 2 Wi, that is what is written here, the maximum efficiency X PFL upon X PFL plus 2 Wi, right. So, this is the all for maximum efficiency of a transformer. Now, all day efficiency of a transformer, it has one formula, we will take one numerical, for that you will understand the thing. All day efficiency is equal to output of transformer in kilowatt hour in 24 hours, right, divided by input to transformer in kilowatt hour in 24 hours, right. So, iron loss constant and constant and present during all the 24 hours. So, whatever iron loss will be there, it will remain constant, and 24 hours, so whatever iron loss will be there, multiply by 24 throughout the day, this much of kilowatt hour, your what you call in terms of kilowatt hour iron loss will get. And copper loss vary as square of the load current from hour to hour varies, right. So, copper loss variable, but iron loss will remain constant. We will see when we will take one example, right. Now, another thing is the voltage regulation. This is very simple thing. The secondary terminal voltage changes, right, with the change in the load due to the change in the voltage drop across the winding resistance and leakage reactance. Because if load changes, then naturally voltage drop on the secondary side will change. So, the right. Therefore, the voltage regulation of transformer is defined as the net change in the secondary terminal voltage from no load to full load, right. So, from no load to full load expressed as percentage of its rated voltage, right. That means, voltage regulation is, this is your V20 the no load, and this is V2FL the full load divided by V2FL into 100, this is the voltage regulation. So, it is the net change in the secondary terminal voltage from no load to full load expressed as a percentage of rated voltage. So, this is my voltage regulation, right. Now, what is V20, what is V2FL? So, your V20 that is a secondary voltage when load is thrown off, that is V20 is equal to E2, that means when load is not there, say say no load condition, right, and V2FL is full load secondary voltage, it is assumed to be adjusted to the rated secondary voltage, right. So, voltage regulation is a figure of merit of a transformer. For an ideal transformer, voltage regulation is 0, because in that case your V20 is equal to your V2FL, I mean same thing, because for ideal transformer, right. So, in that case regulation is 0 for an ideal transformer. So, smaller is the voltage regulation, better is the operation of the transformer, right. So, that means voltage across the terminal of the load will be better, right. Now, if you look into the circuit like this, so this is my E2 is equal to, this is an ideal transformer as if nothing is here except winding. So, this is E2 is equal to V20 and this is Re2 Xe2, your what you call that your secondary resistance and reactance. This is the current I2 and V2 is the voltage across the your load, right. So, assume equivalent circuit referred to this one, then Re2 actually will be R2 plus R1 upon K square, right. So, R2 plus R1 upon K square and Xe2 is X2 plus X1 upon K square, right. So, this is your what you call the approximate equivalent circuit referred to secondary. Shunt branches are negligible, I mean we have approximated it, shunt branch everything is approximated, it is neglected, right. So, Re2 Xe2 expression you know all this, right. So, this is your what you call the voltage regulation. Now, then another one is now for voltage regulation expression for different power factor. Say case 1 we consider unity power factor load. When load is unity power factor, it is purely resistive, right. If it is purely resistive, then your current I2 and V2 both are in phase, right. If these two things both are in phase, right. So, this is my voltage V2 and this is your and voltage drop across resistance I2 into Re2, right. So, and as it is a unity power factor load, so this is my I2 and V2 both will be in phase, right. And this is another thing is the I2 Re2 drop also you add, because E2 is equal to, if you just look into this, that E2 is equal to your V2 plus I2 Re2 plus j I2 Xe2, right. So, as j I2 Xe2 means it will be 90 degree from here to here, and this is my voltage E2 and this is my delta, right. So, that means my E2 your what you call E2 square will be is equal to V2 plus I2 Re2 square plus I2 Xe2 square under root, right. So, that is why your E2 square is equal to V2 plus I2 Re2 square plus I2 Xe2 square, that means your E2 is equal to square root of this one. Now, as an approximation you can write for the E2 now another thing we can write that E2 cos delta is equal to V2 plus I2 Re2, that also we can write E2 cos delta is equal to. So, that is why we have written E2 cos delta is equal to V2 plus I2 Re2. Now, if delta approximately is equal to 0 say, that means cos delta is 1, therefore, approximately E2 approximately is equal to V2 plus I2 Re2, or we can write E2 minus V2 upon V2, right, is equal to I2 into Re2 upon V2, right, or we can write we have just seen no E2 is equal to V20, therefore, V20 minus V2 upon V2 is equal to I2 Re2 V2, right. So, this is the expression of the your what you call the regulation, right. Similarly, for lagging power factor load, this is for unity power factor, for lagging power factor load, that means current lagging power factor load means current is lagging. So, this is my current secondary current I2, it is lagging from V2 by an angle phi 2, right. So, in that case your what you call this is the current is lagging. So, along this it will be drop will be I2 Re2 and then I2 Xe2 will be this one, right, and this angle is 90 degree, look at this angle is 90 degree and this is your E2, this is your E2, and angle between V2 and E2 is delta, here it is delta, right. Now, you make all horizontal and vertical projection. So, this portion look at the cursor, I am not marking by ink, look at the cursor, here will be I2 Re2 cos phi 2, because this is phi 2, this angle is phi 2, therefore, from the simple geometry this angle is also phi 2, right. This angle will be also your what you call phi 2, right. Look at the cursor, you can do it by simple geometry. Therefore, this portion is I2 Re2 cos phi 2 and from here to here it is I2 Xe2 sin phi 2, look everything I have marked, and this whole vertical line this angle is phi. So, it will be your phi 2, so it will be I2 Xe2 cos phi 2, right, and this portion vertical, if you see that this portion I2 Re2 sin phi 2, right. So, this is simply your what you call is simple geometry, you can make it out all these things, right. So, not much to explain, because we have seen your single phase AC circuit, phasor diagram, everything, right. So, with this, if you make this is a, so therefore, this triangle your what you call, if you make it is a your what you call that your right this your this triangle, if you consider, I mean this portion and this portion if you consider, so E2 square will be V2 plus I2 Re2 cos phi 2 plus I2 Xe2 sin phi 2 whole square, right, plus I2 Xe2 cos phi 2 minus I2 Re2 sin phi 2 square, right. So, if you look into this, that if you look into this, that this has been written, this is E2 square is equal to this one. So, from which E2 we will get. Now, as an approximation also you can write E2 cos delta, right, E2 cos delta, I mean this one, I mean E2 cos delta, I mean this portion is equal to my V2 plus I2 Re2 cos phi 2 plus I2 Xe2 sin phi 2, right. So, that is your what we have written here. What we have written here, right, this is the equation. Now, assuming delta is very small equal to 0, so cos delta is equal to 1, therefore, E2 is equal to V2 plus this term, right, or you can write E2 minus V2 upon V2 is equal to this one, you take I2 common, so it will be V2 0 minus V2 upon V2 is equal to I2 Re2 cos phi 2 plus E2 sin phi 2 upon V2, right. So, therefore, base impedance, we have just seen base impedance secondary side, it is V2 upon I2 on the secondary side. So, ZB stands for your base impedance and 2 stands for secondary side. So, ZB2 is equal to V2 upon I2. Therefore, this equation Re2 cos phi 2 plus Xe2 sin phi 2 divided by V2 upon I2 we can write, and that V2 upon I2 is equal to ZB2, right. So, that is ZB2. Therefore, we can write V2 0 minus V2 upon V2 Re2 upon ZB2 cos phi 2 plus Xe2 upon ZB2 sin phi 2. That means, let us define this is RET per unit, that means dimensionless quantity, PU means per unit, right, per unit. So, Re2 upon ZB2 and Xe2 per unit is Xe2 per unit is equal to Xe2 upon ZB2, and I have written here it is per unit. Therefore, V2 0 minus V2 upon V2 the voltage regulation in terms of your percentage, that is Re2 per unit into cos phi 2 plus Xe2 per unit sin phi 2. Very simple it is, just little bit your practice is necessary. Thank you very much, we will be back again.